So good morning, everyone. Thank you for being here in such an early time in the day, and thank you all the GitConf, CommitConf, sorry, all the volunteers and the organizers for, dedicating their time to provide us with this beautiful talk. My name is Salvador Pérez. Spelled S-A-W-A-N-E by Starbucks employees all over the world, which is not exactly the actual, anyway. So yeah, I'm currently working at 20 as a backend engineer, and meanwhile I'm just studying some functional programming to try to sneak some of the features there. Let's see how that goes. And well, the important part of this slide is that we are hiring. So yeah, if any of you want to join us, just go just outside the talk, and left-hand side we have a stand, so you will be able to provide your data and we'll contact you. This talk is about Git internals, and this is the agenda we will have today. First, I will do just a very brief introduction. I will ask you a couple of questions to warm up the audience. And I've split the talk in 3 parts. For the first one, I will talk about the low-level data structures that Git manages. After that, I will provide just a bit of data on some extra, I won't call them data structures, but some extra data Git manages. And after that, I will talk about all the high-level commands you can use and how they relate to those data structures, if time allows it, which, well, we'll see about that. For the introduction, how many of you are using Git in your current work, or have you used in the past? Okay, yeah, most of you. And from all of you that are using it, how many of you did have to clone a repository again after messing up? Ever? Cool. So anyway, Git was built with kind of the Unix philosophy in mind, not because of the Git itself, the Git CLI itself, but because of all the subcommands it contains. So there are lots of very low level that only do one thing and they do it well. And then there are lots of abstractions which use the low level ones. The first ones are called the plumbing commands, and the second ones are the porcelain commands. And that's all for the introduction. This is the directory that you get once you create a new repository or clone one. It will create a .git folder directory, and inside that you will have this structure here. The branches one is, as far as I know, deprecated, and it's only there for purpose of backward compatibility. Hooks and info are important, but I will not delve into those. And finally, these 3 here, I will talk about them, both logs, refs, and objects, but I will focus more on these 2. Yeah, I decided to name this part of the talk just Git as a version file system, because it kinda is what actually happens behind the scenes in Git. Git manages 3 kinds of objects: the blobs, trees, and commits. For the blobs, it is a representation on one file at one given point in time. It will contain the whole content of the file, compressed, so it will be really small because it's usually text. And the name of the file is the SHA1 of the content. I think it has some more details about that. It contains something about the name for salting and everything, but basically it's the hash of the content. Notice that the blobs don't contain any information about the name of the file. It's only the content. It's a dump object, just a dumping ground for the object content. So I won't talk much more about blobs. Here I left you a couple of plumbing commands, the low-level ones, in case you want to delve a bit deeper and just play a bit with it. These are, well, the ones used to get one file and generate the blob object, and the ones to retrieve one. So you can play with those. And we will go into trees. When I talk about tree, the tree structure that Git uses, I'm talking about one node of a tree. So it recursively uses several trees to get the whole directory. It has a very tight structure, internal structure, because this one is not compressed. It only contains data. And contains, pointers to blobs and trees. This is a screenshot for one actual tree in one of my repositories. As you see, it contains, in the first column, the Unix permission tuple with some extra data, which is used to identify the type of object there, even when you have the actual type there. You have here the signature, so the SHA1, with which the object is named after. And finally, here is where Git stores the name of each file and directory, so it can retrieve it later. That's all there is in trees. So when you want to get your whole directory back at one point in time, it will get the top level directory, the top level tree, and recursively all over the different trees, it will get the data back. Commits. Commits do have the very tight representation as well, because it contains as well data that Git needs to understand and parse. I think we will see better what it contains in the example here. It starts with a tree, so the representation, the hash of the tree, and the parent commit. So you could say the whole Git repository is just a graph, and in each node of the graph you contain a tree with the whole version you had at that point in time, because that's what commits are. They are a snapshot of your whole repository in a given point in time. After that, you have two lines that at first seem to be actually the same, so the author and the committer, but there's a very slight difference. The author is the one who actually wrote the changes reflected in that commit. The committer is the one who actually committed them, which is usually the same, but not always. So for instance, when you do a cherry pick, you basically are copying the diff from you introduced in one commit into another. If you do a cherry pick of your own commit, that's no problem. Both will be still the same. But if you cherry pick a commit from a different user, the author will keep track of who was the original committer of those changes, and the committer line will contain info on who did that actual commit. So you don't keep traceability on that. Finally, in these lines, you have the timestamp on when was that commit created. So that's how several tools let you know how many time ago it was created. That's how. And finally, you have the Git message to identify what happened in that without actually looking at the changes themselves. So that's basically all there's about commits. And I kind of lied a bit. There's 1/4 data structure here, not only blobs, trees, and commits. We have the index. The index is kind of, I like to see it as a dumping ground for everything. So it contains a lot of information on optimizations. It contains a lot of info on for instance, what files you did add and they are pending to commit. So all that information is here. It has, for what I've been able to find, it doesn't have a very thorough in-depth documentation on the structure. I found these two links, which you can check in the slides, because I added the link to the slides to the talk description, and I will tweet them as well, so you can just delve deeper as well. And again, I've left you a couple of plumbing commands in case you want to play a bit more. But as I told you, each blob contains the whole contents of a file in a given point in time. And trees references those blobs, and commits references those trees. And to do a checkout, you don't need a network to get those files back, right? So do you keep the whole history of all blobs you have created? So every time you do a git add of a file, you're creating the blobs for those files. So even if you add a file by mistake and you revert it back, and you make some more changes and you add it again, you will have 2 blobs. Are you keeping those? Yes. Yes, you are. Except for some optimizations Git does, which, well, I will talk about them more in depth later, but I can give a sneak peek on those. So for big files that don't change often, let's think about, I don't know, let's assume someone by mistake did add a SQLite database there for testing data. And that database only changes once every month, 2 months because of, I don't know, a change in the schema, for instance, or some extra test cases you need to add to the database. So in those cases, Git will be able to recognize these files are a waste of space. So it will create some structure in which it will hold the last version of the file and deltas to the previous ones. So, well, Git is assuming you will want to use the most recent one more often than the old ones, so it's not that way. And of course, you only see one slice at a time. You will only see one version of each file at a given point in time. I will only go very quick on this. It's not actually an issue, and that's obviously marked as a won't fix, but this can give you a really big headache when debugging it. We have seen it only once in 20. It was a couple of months ago, I think. And yeah, so it's what happens when 2 objects you have created, even a tree and a blob and a blob, commit and blob, whatever, have the same signature because SHA did collide. And there are some funny cases depending on which object did collide with which one. I left here a link where one guy did recompile his SHA1 library to generate a really, really small hash, and just by brute forcing it, generating collisions. And it's really funny to read, so I left it there. But the scary thing is, yeah, this one, that some of the failures are silent, and you will only detect them when another person clones or pulls, and everything will be a mess. Following from that, I will go into the second part, the building up. I will talk here about branches, tags, and logs. Logs are not so well known, but branches and tags, I guess, are. For that part, the branches and tags are stored here. So refs heads is branches, and refs tags is tags. And finally, the logs contain everything about logs, obviously. Talking about branches, at its core, branches are nothing more than one file containing the hash of one commit. That's all there is to branches, with one catch. If you are checked out, we'll see what that means in a very brief moment. If you are checked out into a branch and you create a new commit, the branch will move along, which is a behavior you have already seen, so I didn't discover you, America, but there it is. And this is why Git knows when you are checked out into a branch or why not, or when not. The head. It's a file contained in the .git directory, just in the plain .git, not inside any subdirectory. And it contains a symbolical reference to the last branch you have checked out. So that way, if you checked out master, this will contain master, just the plain word. It's a symbolical reference. It doesn't resolve the actual commit. So that's the way Git knows, okay, I have to move the reference master a bit further when you do a new commit. but it doesn't always contain a symbolical reference because you can check out single commits. So when you check out a commit, this will contain the most symbolical reference it can get, which is the actual SHA1, which is not exactly a symbolical reference anyway. While going through these slides this morning, I did think, and I've never tried it before, so I give it to you as homework, and I will do it as well myself. What if you have a branch with the same name as one SHA1 from a commit, and you check out that commit? It will probably move the branch, but yeah, let's see about that. So yeah, when it doesn't, it does contain the commit hash. Yeah. After that, yeah, I will go outside. I will skip tags for a moment and talk about logs. Logs is a really, really unknown and really, really useful feature in Git, and it's because it contains everything that has happened in your repository. Whenever you pull, whenever you fetch, whenever you merge something, whenever you do even a git add on a file, this is logged here. And if you realize from the structure, these refs heads kind of resembles to these ref heads here, and the refs remotes origin references this refs remotes origin here. So exactly, it will split the logs depending on which branch you are checked out at a given point in time. So if you mess up again with your repository, you can come here and see, okay, what did I do that went wrong? And you will see everything. So you can fix it, which is great. You don't have to pull to clone all over again, which is really, really good. And on top of that, Git uses these logs to provide you some extra functionality. I will, if I have time, I will show you nearly the end. After that, yeah, now we have completed our detour for logs. I said I was going to go only briefly over them, and I will move to tags, which is not a very exciting topic anyway. Tags are like branches, but they don't move. That's all there is to branches, well, with a couple of catches anyway. There are two types of tags. The ones called the lightweight tags, in which, yeah, it's only a file containing an object SHA1. And notice I didn't say a commit SHA1. You can do tags on blobs. You can do tags on trees. You can do a lot of black magic with that. So for instance, you can have some objects committed into Git, because if you have a tag pointing to it, Git will upload those objects, but you don't have them in any working directory. So debugging scripts you don't want in the final version of the program, you can have them apart, and you can just get them out with pulling out the tag, or whatever actually you want to think about. After that, the annotated ones. Annotated tags resemble more to commits. So the annotated tags contain kind of the same structure as a commit. It contains the author, it contains the timestamp, it contains a commit message, which is why they are called annotated, because they have the message on what you are pointing to, which kind of helps if you're not pointing to a commit, right? And yeah, the object type and a reference, obviously, to the object. Now I'll move to the remotes part of it, in which, well, a remote, we know that Git is always defined as a distributed version control system. So what does this mean? This means that there's not a central repository where it doesn't have to have a central repository from where you pull all the changes and you push all the changes, and there's nothing more on the sides. So let's take as an example Heroku, the deployment platform. To be able to deploy into Heroku, you just need to make a push onto the Heroku remote. So in that case, you would want to have two remotes. You can have origin, which will point to GitHub, Bitbucket, whatever you like, and you push there your code. And then after that, once you want to deploy, you just push to the Heroku remote. And you can, in a very weird scenario, you can even have a remote pointing to a peer repository, and it should work. I don't have any case in mind why you would want to do that, but yeah, you can. So yeah, the remotes are configured in the .git/config, and they are configured like this. For each remote, you will have the URL of where the whole repo is being kept, and then a bunch of ref specs. By default, it will only create one. I think it's the first one, well, with an asterisk here anyway, not only master, and an asterisk here, not only master. But this basically tries to represent the fact that whatever you find in your remote origin, the remote you called origin, the reference master will be pulled into your dev master. So in your local, the branch will not be called master, but it will be called dev/master. So you can do a lot of things there. The one by default substitutes the dev master by an asterisk only. And if you have only the fetch one, the fetch and the push will be symmetrical. But push tag here, which will say, okay, but when I push master, I will push to dev master. For instance, this is a very, very silly example, and this is not from a real repo. I did just make this up for the purpose of the talk. But anyway, also, you may have noticed I have a plus here, and I don't have a plus here. That's a very subtle difference, and what that means in Git terminology is that in the ones with the plus, you are allowing it to pull from that remote into that branch, even if the changes are not fast forwarding. So even if you have to actually merge and solve conflicts, it will pull and it will merge into your local branch. If you don't have the plus, it will not. It will say, oh, this is not a fast forward, I'm not going into there. So that's something you may find useful to be able to avoid those or losing changes or having merge conflicts when you didn't want to just by pulling. So that's a very useful thing here. And anyway, we are moving finally into the optimizations Git does. I will only talk about a couple of them. So the one that is not in the slides is about the objects directory. So I told you, every tree, every object, every commit you have ever, they are dumped into the object directory. That means that once you have a repo, I don't know, with commits for over 5 years, you will have really huge amount of files there. So once Git notices, oh, this is really big, and searching for a given reference in one of those directories with a lot of files will be really expensive. So it will just make an optimization, and what it will effectively do is taking all the hashes, take out the 2 first characters, and create a directory with that name, only the first 2 characters, and then moving the whole object inside, removing the first 2 characters. So effectively, the lookup will be exactly the same, but you will be narrowing the search bit by bit. And if one of those folders, directories, already contains a huge lot of objects as well, it will apply that again and create more subdirectories with 2 characters and move the blobs inside. So searching will be much, much faster. Then moving on to packed refs. References, that's where the name comes from, are, as I told you, branches and tags. That's all there's to, well, and remotes, the remote branches anyway. Once Git notices, oh, you have lots of references that you are never changing. You have tags made in 2005, and we are in 2018, and it's pointing to the same object. So there's no point in keeping that in its own file, because, again, it slows down the search. It will do the same for branches. So what Git will effectively do is creating a file called packref, which will be in the .git directory, and it contains a list of hashes hashes of the object the branch is referencing, the branch or the tag, and the name of the tag. And it will be ordered by the name of the tag, so it will be much, much easier to look for one of the references and pull the reference back, the hash. And finally, the the pack files. This is what I told you about before. The ones containing the last snapshot of an object and deltas to the previous ones. Git will do this automatically every time you push, if I recall correctly, and every time you do a git gc. So for the ones of you that don't know what gc is, when you run git gc, Git will just sweep over all the objects you have in your .git directory and just check, is this object still referenced? No, I'll delete it. When will an object stop being referenced? So for instance, when you do a git add and then reset it because you didn't want to add that file, that object will be orphaned. Nothing will point to that object unless you create a tag. So those blobs will be removed when you do a git gc, and these pack files will be created at that point in time as well. So yeah, that's a very neat optimization you will have by harnessing the power of Git. And finally, I'm not sure how much time I have left, but anyway, I will go up to the point I can. I will go over some high-level commands, and I will try to show you how it maps to each of the data structures here. So starting by git diff. When you git diff, you just basically get two references. You unpack all those objects. So for instance, you get one branch and one commit, for instance. So you are diffing the point in time pointed to by that branch with the point in time pointed to by that commit, or two branches, or whatever you want, actually. So Git will unpack all those references, regenerate all the directory structure, and just diff file by file. So it will basically show you the diffing of those. By default, if you just run a git diff, it will run your current status with all the changes you have done, your working directory, with the unpacking of the reference you have in the head. The file we talked before about the last branch you committed, you checked out, or the last commit you checked out. So it will unpack that, and it will compare it with your working directory just by diffing, the normal diffing. After that, we have the git reset hard. If you haven't ever heard about it, git reset hard just takes your current branch and it moves the tag, because we showed the branch is only one tag, one reference. It will move it to wherever you point it to. So if you do a git reset hard master, it will move your current branch to master, and that will be all. Well, it will actually unpack whatever is in master because you are actually moving and checking out to that point in time. But all there is to it is moving the pointer. And you will lose, when you do the git reset hard, you will lose all your current changes in the working directory. So not only the changes in the current directory, but the changes from the branch you are now moving to the branch you are now in before running this. All those changes in the middle, they will be ignored and removed. As opposed to that, we have the reset soft. This is the default reset. If you don't need to write the -- soft, it's just git reset. It will basically move again the pointer to the branch you have told him to, or moving the branch to the commit you have pointed to, and it will diff the origin and the destination and let you those changes as uncommitted changes. So you can, I don't know, I usually, for instance, when I use this, is because I did a lot of WIP commits, because I was working on that, and at the end of the day, I just committed whatever I had, and after all that development cycle, I said, this repo is a mess, this branch is a mess. Okay, I will go back by keeping all the changes, and I will redo the commits in manageable bits. Or for instance, when you have, God forbid it, a really, really big code review, and your code review tool doesn't allow you to, because, oh, actually, you're trying to get inside 10,000 files, and we are limited to 700. So you can go back and say, OK, I will commit this 700 by 700, and just one code review for each, for instance. That's not a very common use case, and I hope you don't have to do that anytime, but that could be an use for that. Yeah, checkout. When you check out a branch, well, the first thing it will do is writing your reference into the head, which makes sense because that's what the head is, and then it will unpack the object. So it will the reference by the branch, what commit is pointed to by the branch name. From that commit, it will take the top level tree. It will recreate the objects, go inside all the subtrees, and do it again and again and again recursively until you have the whole repo again. Merge. Merge is the first interesting command because we have two cases here. For the first one, well, I'll skip that. Well, not really. For the Git merge, what Git will effectively do at first will be to calculate the first common commit between the two branches, the one you are trying to merge and the one you are trying to merge into. It will calculate the most common ancestor, and there's where the two cases are. First one is you are trying to merge a branch that came out from the branch you are trying to pull it, to merge it into. So actually the most common ancestor is the commit you are in right now. So that's the first case here, in which you are trying to merge test into master. I have a typo here, sorry about that. The green commit is this one and the head is here, but for the rest of it, it's good. So what Git will effectively do is, okay, what's the common ancestor between this one and this one? Okay, it's this one. So what should I do? Just move the tag, and you have committed it. You have merged it, sorry. This behavior is called the fast forwarding, and that can be avoided. Why I say that? Because in some projects, in some companies, you prefer to keep traceability on when did you merge and what changes were introduced there. If you do this, you are just introducing n commits here, which you don't know when that feature started, when did it end. It's just there, like if you committed straight into master. You can avoid this behavior, as I said, and create a merge commit here by running the git merge with no FF. So that will avoid the fast forwarding behavior. And it will behave like the second one. So we have commit at the tip of one branch, which I will call commit A, and we are trying to merge it into branch commit B. So the most common ancestor is not B, but another arbitrary commit called C, which is basically this status here. Once again, sorry about that, but the green ones and the head should be in the master branch, which is a shame, but yeah. So what Git will effectively do in this case is just basically creating a whole new commit, which is called a merge commit. And this is actually the reason why the structure that Git uses for the top level commit referencing is not a tree, but a graph. Because the commit that Git creates has two parents. Both commits, the one you are merging and the one you are merging into, are both effectively parents from the commit you are creating, the merge commit. So this commit here is making it not be a tree because you are merging leaves, and that's not allowed. So this makes Git a graph of trees, not a tree of trees. After that, I'll move into the cherry pick, which I talked about it before, but I didn't actually explain how it behaved. I just referenced it. Git cherry pick will effectively get all the diff between the commit you're trying to pull and the previous one, and just try to apply that diff on the branch you are into, on the commit you are right now, on your working directory. If that works, and there's no merge conflict, you are good to go. The commit is created, the committer is updated, the author is not. The merge, the commit message will be kept the same. So all that changes is the parent, because now the parent is a different one, and the committer. So it's that case. We have this commit here, and we want to pull it here. So, bam, it's pulled. It didn't have any merge conflicts. By the way, I forgot to mention, in the index file I was talking about before, the one with no reliable documentation on what the structure is, whenever you have a Git conflict, when you merge, you rebase, or you cherry pick, a flag is added there so that Git knows you are in a merge conflict right now. That's one of the thousands of things Git does with the index. After that, we will move to another interesting command and one related to merge, kinda, and it's the rebase. And sometimes there's a confusion on when to use a rebase, when to use a merge. I think that boils down in the end to your own preference, your own choice, and the choices of your company, and how much traceability you want to get, and lots of things. But what it effectively does, what the behavior is, so that you can relate to that after this, is basically it starts the same as a merge. It calculates which is the most common ancestor. In this case, it's this one. And then when you try to rebase this branch onto this one, it will just calculate the diff between the first two commits and then try to apply here. That goes well, that's perfect, we will continue. If that doesn't go well, you will have a merge conflict here, you will have to fix it, and then it will continue. What will do it after? Calculate the diff between these two and add it after that one. So that's why when you rebase a branch and you have a merge conflict in the first applying of a diff, you will probably get the same conflict or more bizarre conflicts as you move forward and you continue applying more and more commits after that. And the ending result will be here. These are the two commits we have rebased. The branch is kept the same, but on top of the other one. And these two commits I gave a kind of grayish color. Those are left unreferenced. There's nothing pointing there. Well, maybe at first the origin counterpart for that branch, but after you push, forcing the push, these two will be kept unreferenced. So the next time you do a Git garbage collector, those will be removed. And yeah, as for uses of rebase, I would suggest once you have finished coding a feature, you have all your tests passing, you are 100% certain that the feature is working, but in the meanwhile, someone has finished his own feature or a bug fix or whatever. I usually prefer to rebase my branch first, check that the tests are still passing, that no one broke anything in between, and only after that, I will just merge into the actual branch master, and I will probably do it with no FF so that I don't lose traceability on that. But that's just my way of using it. It's not set in stone, and everyone has his own opinion and likings. So that's just an opinion there. And I have some more, which I will skip because I don't have, I think, much time left, and I would like for some questions to be asked. So I will just go briefly over this one. You can actually do that. This is a valid Git command. And this will be done by taking a look at the logs for that branch. So when you try to check at a point in time in Git, in a branch, it will go to the logs for that branch and check what was the status of that branch 1 week before, or there are several instructions you can give it there. And it will actually check out to that point in time. So if something broke, I don't know, 1 month ago, you can go to that point in time when it broke, and you can see what happened there. which is kind of cool. And I think I'll go into the questions now because, yeah, no much time left. So thank you for listening, and I hope I didn't bore you too much this early in the day. Yeah, sure.
When you use garbage collector, the fixes are applied to the remote or just the local version?
The fixes are applied into your local directory. So the fact that you are running garbage collector doesn't mean you want your peers to, or your peers want your garbage collection to be applied to them. Maybe one blob you don't have referenced, they actually did a tag on that blob. So you don't want those changes usually to be propagated. I think there's a way to push those changes as well, but I'm not sure what the command was for that. But I'm sure you can push that to the remote. Sorry, the question was if the changes you are getting by running the garbage collector are applied to the remote or only the local development directory. Sorry, the question was if the logs are stored in remote or local. Come on. I will go faster, sorry. Well, actually, I can use any of these. Okay, so if you see there, inside the logs directory, you have the remotes subdirectory. So yeah, effectively, you will have here the logs for all your remote branches. Mm-hmm.
How do you solve the SAUH1 issue?
It depends. So usually you can, for instance, if the merge it depends. So if the conflict was when you created a blob, you can add a space at the end of it, at the end of the file, and just commit it again, and it will be fixed. There are more tricky cases like if a commit conflicts with another commit, or if a tree conflicts with another tree. That's a bit more tricky. For instance, for fixing trees, you can add an empty file again, and so there are only tricks to fix those. There's not a given procedure. You have to identify what the case you are in, and actually in the link I provided, you have cool ways to identify in which case you are in because of the way it failed. So that can be an option. But yeah, you have to figure your way out. Yeah? Yeah. So the question is, if you are using a continuous integration tool and your commit is marked as green because all the tests passed, what would happen if you rebase and it is kept as green, but it is no longer green? So one of the contents of the commit object is the reference to the parent commit. So once you rebase, the parent changes. So the whole commit is replicated. You have two commits, the one that was marked as green with the same reference it had, but the new one with a different reference. So the CI should be able to identify this is a different commit, and actually it is no longer valid because in the point in time you are now, when you have applied it on top of that, it is making some tests fail or whatever, so it is no longer green. So it's good that it marks as red, and that's done because of the commit hash. It doesn't mark the merge as red. So the question was, what if when you merge, the continuous integration doesn't mark the new commit as red and it is kept as green? So it depends. If you had your branch with a merge with a fast forward, it's because it was already at the tip of the branch you are merging into. So it should still be green because the status of the repository is exactly the same. In the case in which you are merging with non-fast forward because it was at another point in time, well, the merge commit will have a different signature again because it's it has two parents, and the hash of the content of the blob, of the Git object is different. So it should be able to identify that it is read because of the same of the commit signature. But anyway, if you want to avoid that case, by all means, just rebase first and then merge. Don't pollute the parent branch. If you didn't push the changes to the remote, I guess you should be able to fetch those changes again. In local, I think when you garbage collect, you garbage collect. It's yeah, we are all grown-ups. And yeah, so if you ever want to contact me, not only about Git, but yeah, whatever you want, that's my Twitter handle. And well, you have the slides available at the talk description. I just updated it, so you will have a link to these. So well, thank you very much.
Thank you.